Hello, my name is Karl Schmeckpeper, and I will be presenting our work, Learning Predictive Models from Observation and Interaction. Can we teach robots to use tools more effectively by using unlabeled videos of humans using tools, which illustrate how a tool should be used, and data of robots interacting with their environment but not using tools, which should be enough to infer how the robot's actions affect the environment? Videos of humans are a broad source of data that is largely untapped when learning robotic perception and control. Unfortunately, using human data is difficult because it lacks actions and exhibits substantial domain shift to robotic data. However, despite these difficulties, videos of humans are still a potent source of information. A broom will push objects, whether it is held by a human or by a robot. Object interactions, environmental properties, and physics remain constant regardless of the source of data. We approach this problem in the context of learning an action-conditioned prediction model that can be used in model-based reinforcement learning. Typically, these prediction models are trained with data from the agent's own interactions with the environment. Collecting this data requires the agent to have a policy that can reach interesting configurations, which can be difficult. We aim to learn prediction models from action-free data, such as videos of humans, to enable difficult behavior, such as using tools. Next, we will describe our approach. We learn an action-conditioned video prediction model from two kinds of data. Interaction data of an agent interacting with its environment, containing both states X and actions A, and observation data of a different agent interacting with the environment, which only contains states X. We use both kinds of data to train a predictive model, which can be used for action condition prediction and planning on the original agent. We formulate the problem with the shown graphical model. States x1 through xt are generated from the previous states and a latent action z1 through zn. The latent actions are dependent on a domain variable d. At each time step, the states x and the domains d are observed. The action A is observed for interaction data, but not for observation data. We instantiate the graphical model with the shown architecture. To optimize the evidence lower bound, we predict the latent action zt from the state xt and the state at the next time step xt plus 1 using the inverse model. When the true actions are available, we additionally predict the latent action from the true action at using the action encoder and encourage the predictions from the action encoder and the inverse model to be similar with the Jensen-Shannon divergence loss. We additionally constrain the predicted latent action with the Kullback-Leibler divergence to a prior distribution and by decoding it to the true action when available. The next frame, xt plus 1, is predicted from the latent action zt and the current frame xt, and is trained with the L1 loss on the prediction error. We implement the system with deep neural networks. We use a variant of stochastic adversarial video prediction as the prediction backbone, fully connected neural networks for the action encoder and the action decoder, and a convolutional neural network for the inverse model. We handle the domain shift between agents with a partitioned latent space. We partition our latent space Z into two components, Z shared, which captures the part of the latent action which are shared between domains, and Z domain, which captures the unique parts of the latent action. We enforce this separation by learning the same prior, Z shared in all domains, and a different prior for Z domain in each domain. We use the Kullback-Leibler divergence to enforce these priors. Now we present our results in the driving domain and in the robotic manipulation domain. We apply our approach to the driving domain using the new scenes dataset. Given a dataset of driver actions in video and a dataset of only dashcam video, We learn an action condition prediction model. We compare our results top to a baseline approach and stochastic adversarial video prediction bottom. We also investigate the robotic manipulation domain. Given a dataset of random robotic interaction data containing observations and actions, top, and observation data of humans containing only observations, bottom, we seek to learn improved prediction models that will enable improved manipulation performance. Our model is able to predict latent actions that can then be decoded to reasonable actions in the robot's action space from both human and robot observations, despite never seeing human data labeled with actions. Our model improves upon the prediction performance of existing approaches. We compare against stochastic adversarial video prediction, or SAVP, and compositional latent action space predictor, or CLASP. Our model is able to successfully leverage human videos to improve prediction performance on the robotic data. We compare the predicted video sequences between our method, top, and SAVP, bottom. Our approach generates more realistic predictions, especially when interacting with objects. The improvements in prediction allow the planner to choose better trajectories when combined with our method, top, in comparison to SAVP, bottom. The differences in predictions and plans translate into noticeable differences in manipulation success between our approach, left, and SAVP, right. We also present additional examples of our model successfully completing manipulation tasks. The predicted trajectories are shown left, while the executed trajectories are shown right. We were able to create an action-conditioned video prediction model that can learn from action-free and action-conditioned data. This model can use videos of humans to improve robotic control. Thank you. Please visit our poster session for additional information.